In this video, I'm going to talk a little bit about index raising and lowering. And so uh, this is really a big thing in working with tensors and doing tensor algebra and tensor calculus and so forth. Is this switching between different vector spaces? And so what I have shown right here is that it's not necessarily the case that these covariant vectors and these contravariant vectors are going to be the same thing. It can be the case, for instance, if you are in a Euclidean space with an orthonormal basis, but for the most part, it's not going to be the same thing. So this one here is a covariant vector, and this is a contravariant vector. Or they are the covariant and contravariant components of vectors. And so covariant vectors live in the dual space or covector space, where the contravariant components are in the vector space. And like I said, this playlist is somewhat of a more for intuition and non-rigor, so I'm not going to sort of rigorously define like a dual space and a vector space. I will talk in the next video a little bit about the difference between those two things, and particularly how that applies to using derivatives as your components and your bases. But for now, just know that a dual space and a vector space are not the same thing, and so you can't just set them equal to each other. And so we actually have to use the metric tensor here to lower one of the indices. And so we can see here this metric tensor here acting on this contravariant component turns it into a covariant component. Like I said, if we are in an orthonormal Euclidean space, then the metric tensor is just going to be the identity matrix. And so in that case, in that specific case, you could set these equal to each other, but in general, you cannot set those things equal to each other. And so here I actually have it written out in sort of the matrix form. So I have our covariant vector here and our contravariant vector here. And this covariant should actually be as a row vector, but like I said, this is non-rigorous, and so I'm just doing it like this essentially because I like the way it looks better uh, for for our purposes here. And so essentially what I have here, so if we are looking for the first component here, which would be this one right here in our contravariant vector, then we have to run through this summation here, which is just taking this one times this plus this one times this plus this one times this. And so that's what I have right here. And so you see I have the G1J, and then these are the bases for our metric tensor. Then we have the VJ, EJ, which is the vector with component multiplied by its basis there. And so this is how it looks as a summation right here. And so then I have expanded it out explicitly here. So we see that we run through the j's, so we're summing over j, and so we have j right here and down right here, and we have j right here and down right here. So we see that it goes from 1 to 2, then j right here and down to here, and of course on our component here as well, and this G13 here is actually part of the component. That G13 would just be a number. That's the component of the metric tensor, where this E1, E3, or the E1, E2, or the E1, E1, those are the bases from our metric tensor. And so then what happens is, so this E1 here, this E2 here, and this E3 here, both, well, those will just be equal to 1, and so I actually put them here as these Kronecker delta with 1, 1, 2, 2, and 3, 3, which just means that it comes out equal to 1. And so we end up with this down here, where the parts in red, green, and blue are just going to be numbers. Those are components. And so then I took out the actual basis part of it. I took out the e's. So this number plus this number plus this number. Then I set it equal to this. This is just sort of the Einstein summation version of it. See, we're summing over the two j's here. And so this number, well, these numbers here added together, so we add these numbers together here, that will give us this number, and that is the first component here of our covariant vector. And so then I just did the same thing here with the second component and the third component. And so you can kind of see just from this, this is just lowering the index of a rank 1 tensor of a vector, and you can see all this sort of summation and adding together and stuff you have to do, and that really tells you why this Einstein summation convention, why Einstein sort of jokingly said it was his greatest contribution to physics. So we have our VI equal GI J V J. So that is the Einstein summation convention, where if you see an index in the lower part and in the upper part, it is implied that you are summing over those. So it's implied that that what you actually have is VI equals, well, actually I'll put the summation here, so j equals 1, and in this case I did it up to 3, and so g I j v j, and so you are summing over the j's. But when you see it in this form right here, the Einstein summation form like that, you can just assume that you are summing over the j's, and so that's actually what I have shown in each of these three things. So we see I put the summation here explicitly, and so we are summing over the j's on all of these. And so we see on the first letter on these g's here, I have 1, then 2, and then 3, because we do a sum for each of the i's here on j, because we need we need 1 for each I on here, because we need a summation for each component of our new vector. And you could do the same thing to if you wanted to switch, if you wanted to go to, so if we had vi, that would be gi j v j, and so this is just switching back from the covariant to the contravariant components. And so yeah, that is doing it for a vector. And so I actually have some examples here. So this example is if we are in the orthonormal Euclidean space, where we just have ones going down the diagonal on here, and so we just end up with 2 for our top one, then 4 for our middle one, and 3 for our bottom one, which is exactly what we have in our original vector. And so we do end up getting this equal to that. But if we have a metric tensor that looks something like this, where we have off diagonals and not everything is equal to 1 in it, then we end up having to do some summations. And when we go through that, we will end up with something that is not equal to the vector that we are lowering the index for here. And so that's just to show that it's not necessarily the case that that those two things will be equal to each other. All right, then down here I have an example of lowering an index on a rank 2 tensor. So I have this rank 2 tensor, this TKL, and we want to lower the second index. We have TKI, and we will do it using something like this. So this TKI is equal to this GIJ acting on this TKL. So here, and I actually kind of spoiled it, I already turned that L into a J, which we can do because we're using it as a summation index. And so we end up with our GI1 times TK1 plus GI2 times TK2, and then GI3 times TK3. And so here, what I'm doing is showing that, so we have this GIJ TKL, then I put the bases explicit here. So if you have downstairs bases on your components, then you have upstairs indices on your basis, and then the opposite here. So if you have upstairs indices on our components, we have downstairs on our bases. So I just put the bases for the metric tensor and then our rank 2 tensor here explicitly. And then over here what I did is I actually split up the component of the rank 2 tensor into an A here and a B because we have this one sort of going with that that basis there, and this one going with that basis there. And so once again, so L equals a summation index. So here I wrote that we can change this L, which I put in red, into this J here, and therefore we have this GIJ, and then we have this AK, and then this BJ here, which goes with this J. But we already have this J here from the tensor, from the metric tensor, and so we can take these two things and we sum over them, and we end up getting this Kronecker delta here. And so this blue J here and this red J here, so when J equals J, then it will be 1. But we sum over that, and that J in the upper index there kind of goes to the components here of our metric tensor. And so then we end up with this. So we still have our A, K, and EK, but now we have this B, J, and then this E, I. So this contravariant basis and a contravariant component. And so what we can do is actually, we can actually lower this index here. And so we end up with our BI as a contravariant component, with our EI as our covariant basis. And so if we take our AK, EK like this, and our BI, EI like this, we can then form that back into, well, we can pull the components out like this. Now we have the components and the bases separated like that. And this AKBI is just equal to this component right here. And we have explicit here our basis. But if we just make the basis implicit, now we have the TKI, which is exactly what we wanted to get. So that was exactly what we were trying to get right here. And so that is how you transform or lower an index on on our rank 2 tensor. And it'd be sort of the same thing if you do higher rank tensors. You just kind of have a lot more things like this A, E, K kind of coming along for the ride. But if you're lowering a single index, then you're essentially just doing this same thing that I did here to here and here. So these steps here just on a single component. And so that is how you lower an index on your tensor. And so once again, it is not the case that our t k, I think I use L. It is not the case that this is equal to our t k I. So the fact that this L tells us that, well, the fact that both of these are upstairs tells us that both of them are contravariant vectors, and this tells us that we have a contravariant and a covariant vector. So the TKL, would have these with our little tensor product there, would have these bases here, and our TKI would have our EK, then our tensor product EI in the upper part there. And so this right here is looking for a covector. So that's a vector that has downstairs indices, or sometimes you see it written like that. And this one is looking for a vector if we are thinking about tensors as bilinear mappings. And so here I just once again put all of the component calculations. So this TKI in 3 dimensions, we'd want to run through each of the K and I through the numbers. So right here, these 3 is with K equal to 1, but then we're going I1, then I2, then I3. Down here, we do the same thing with the I's with K equal 2, then K equal 3. And I'm not going to go through each of these. This is mostly just to show why, once again, we want to do that Einstein summation convention, because this is all the sort of summations that you have to go through in order to find each of these components for our new rank 2 tensor. And so yeah, you can see that you're adding together each of these things, sort of going through each of these over and over again. So yeah, there's a lot of calculations, and you could spend a lot of time writing, and so that's why people just prefer to use the TKL equals G I J T K I, or actually that should be the other way around, shouldn't it? Sorry, should be T K I equals G I J T K. Draw a better K than that. K K L. And so this here, this in the Einstein summation convention is well, it's telling us the same thing as all of this. So that's why people like this Einstein summation convention. And so then I just kind of did the same thing here, putting it in matrix form. So this is those components, and then this is each of those summations just put in matrix form. And so once again, it just goes to show why this Einstein summation convention is so popular. But anyway, I hope you found this video helpful on the index raising and lowering, and I tried to sort of dig into the meat of it a little bit here, looking at these sort of explicit summations and so forth, where it seems like, to me anyway, a lot of sources that you get on this sort of just go through this and say, oh yeah, you can, raise and lower indices, and, isn't that interesting? But they don't really tell you what's going on. And anyway, that was kind of what I was hoping to accomplish in this. That was what I was hoping to sort of add to the conversation as it pertains to, learning about tensors. But anyway, in the next video, I'm going to talk a little bit uh, about how components and bases can actually be derivatives. And what I'm going to do in that video is going to be sort of a quick look at it. If you want a longer and more detailed look at it, I highly recommend checking out the video the video playlist by eigenchris, which I've been putting in the description of all these videos, because him, Andrew Dotson, and this other guy, I think it's like XylyXylyX or something like that. Anyway, those I'm putting links to their playlists on tensors in the description down below. Eigenchris is is by far the best one I found for people who just are just learning about tensors. So if you get past my sort of intuition videos and you want an even deeper dive with a good amount of intuition, Eigenchris is a great place to look. And in fact, when I do my next video on the derivatives as components and bases, it's essentially just going to be me sort of summarizing what Eigenchris is doing. But anyway, I guess I could say, if the only thing my videos accomplish is getting people to find these other great resources, then I'll consider that a win. But I hope you did find this video helpful. Maybe I filled in some gaps that some other places tend to leave unfilled. And anyway, I'm just kind of rambling now, so I hope you found this video helpful, and I will see you in the next video.